Hello everyone. Kotongwane, the native god here. In this session, we'll be looking at heat, right, which is a module in engineering science N4. We'll particularly look at heat expansion for solids as well as liquids. Now, before we carry on, I would like to mention that the topic is generally called heat expansion, but we look at both expansion as well as contraction. Right now, for elements where heat is being gained, they tend to expand. So elements that gain energy or that gain heat energy, they tend to expand, and elements that lose energy or lose heat energy, those ones tend to contract. Now, that is important because it influences how we look at the change in temperature, right? So whenever we need to calculate the change in temperature, right, for elements where heat is being gained, right, the change in temperature will be T2 minus T1, right? That is when heat is being gained, right? And then when heat is being lost, the change in temperature we calculate using T1 minus T2, right? So this is for heat gained, right? And then this is for heat lost, right? So again, when energy is being gained, right, so when the temperature is actually increasing, this is how we calculate the change in temperature, right? T2 minus T1. And then when the temperature is decreasing, hence heat is being lost, how we calculate change in temperature is by using this formula T1 minus T2, right? Now, that is to say that this we use for heat expansion essentially, and then this we use for contraction, right? Expansion means depending on if you're looking at the element or the material you're looking at from a linear perspective, or from the area perspective, or from a volumetric perspective, right? But when an element expands, it increases, right? If you're looking at it linearly, it increases either the breadth, width, or the length. And then when it increases, right, so my point is here, it doesn't matter what perspective you are looking at it at, right? Either way, it is going to increase in length, right, or in area, or in its volume, right? And then when we look at it from a perspective of contraction, right, when something contracts, it means it is decreasing either in length or area or in its volume, right? Right. Now let us familiarize ourselves with the formulas we are going to be using. Now in N2, we looked at linear coefficient of expansion, and then in N3 we looked at both linear and area coefficient of expansion. In N4 we introduce you to volumetric coefficient of expansion, right? Now just a slight reminder of what we looked at in N2 and in N3, right? Under linear coefficient of expansion, right, this is the formula we use, right? This formula is as follows, right? If you have to calculate the change in length, right, be it the material or the element is expanding or contracting, right, we use this principle for linear coefficient of expansion, that essentially is as follows, that the change in length is directly proportional to L, which is the original length, times the change in temperature, right? Now, to get a formula out of this, or to get a mathematical expression out of this, we need to replace the proportionality sign with an equals to sign, right? In order to be able to do that, we have to introduce a constant. Now, the constant for linear coefficient of expansion is this one, right? So we replace the proportionality sign with the linear coefficient of expansion coefficient, which is this symbol, right? So do not mind that these symbols look the same. They don't necessarily represent the same thing. So here, this symbol represents the proportionality symbol. Here it represents the linear coefficient of expansion, right? We use the symbol, it is known as alpha, right? So essentially we replace the proportionality sign with this constant, which is known for linear coefficient as the linear coefficient of expansion, right? Which is this symbol here, right? This here is essentially its, we can call it its unit of measurement, right? It is in per degrees, right? So in replacing the proportionality sign, we then get this formula which we can use mathematically, right? And then this formula is as follows. Change in L is now equal to the linear coefficient of expansion times the original length times the change in temperature. And then of course, change in temperature, how you express that depends on if heat is being lost or if heat is being gained, right? And then we get in N3, we looked at the area coefficient of expansion, right? Of which the area coefficient of expansion is beta, this symbol beta, right? To get the mathematical expression of the area coefficient of expansion, this is the principle that we use, which is as follows, right? Change in area is directly proportional to the original area times the change in area, right? So again, to get a mathematical expression out of this, we need to replace the proportionality sign, right, with a constant, and that constant for area coefficient is the area coefficient of expansion, which is this beta. Hence, we then get the change in area is equal to beta, which is the area coefficient of expansion, times the original area times the change in temperature. Again, change in temperature depends on if the element is expanding or if it is contracting, right? So meaningly if it is losing heat or gaining heat, right? Now, if it happens that we haven't been given the area coefficient of expansion, right, but you are given the linear coefficient of expansion, you can use this expression to get the area coefficient of expansion. So beta, which is the area coefficient of expansion, is equal to 2 times the linear coefficient of expansion, right? Now normally these symbols or these constants you are given at the back of your question paper under what we call constants, right? It normally comes just before the formula sheet, right? So either you'll be given this or that in the statement. If it is not in the statement, then check the constants at the back of your question paper, right? And then of course we get volumetric coefficient of expansion. The symbol thereof is this one, which we know as gamma, right? It's a funny looking Y, right? It is known as gamma. It is known as gamma, right? Now, like just like linear and area coefficient of expansion, right? This is the principle that we use, right, to derive the formula that we use for volumetric coefficient of expansion, right, which is as follows. The change in volume is directly proportional to the original volume times change in temperature, right? And then again, to get the formula that we can use for volumetric coefficient of expansion, we replace the proportionality sign with an equal to sign by introducing this constant gamma. And then you get, as a formula, you get change in volume is now equal to gamma, which is the volumetric coefficient of expansion, times the original volume times the change in temperature, right? And then just like with beta, if we haven't been given the gamma, right, and instead we have the linear coefficient of expansion, this is how you can get gamma, right? Gamma is 3 times the linear coefficient of expression, right? Now let's just look at an example, right, of how you would deal with such problems, right, by looking at this question. All right. Question 7.1, in your own words, states Gay-Lussac's law. Now, Gay-Lussac's law falls under what is this? Gas laws, right? Which we will get to later, right? Now, gas laws we will do later. For now, let us just look at 7.2, right? And then once we have covered gas laws, you will know how to state Gay-Lussac's law, right? Or maybe for interest's sake, let us state Gay-Lussac's law. So Gay-Lussac's law, right? Now this one states that, so this one is in terms of the volume, so states that if the volume of a given mass of gas, remember I said this is a gas law, so it only applies to gases. Mass of gas is constant, right? The pressure it is subjected to is directly proportional to the, or let's say directly proportional to its absolute temperature. Right, so now we'll dive deeper into this when we look at gas laws, but Gay-Lussac's law essentially states that if the volume of a gas is constant, right, the pressure it is being subjected to is directly proportional to the absolute temperature or its absolute temperature, right? This you are able to express mathematically as well, right? Mathematically, essentially, this would be what is this? This would be P1 over T1 is equal to P2 divided by T2, right? This is how you express Gay-Lussac's law mathematically, right? And then here, for interest's sake, we use the capital letter T, right, to show that the temperature is an absolute temperature. So for absolute temperature, we use capital letter T, right? Anyway, let us look at 7.2. So 7.2 reads as follows: a copper rod has a length of 450 millimeters at 30 degrees, right? Calculate the final length if it is cooled to 25 degrees. Leave your answers in millimeters, right? Now, like I said, it is very important that you, in problems based on heat expansion for solids or liquids, it is important that you establish if heat is being gained or if heat is being lost. That will allude to how you will calculate change in temperature, right? So here they clearly say that this is being cooled to negative 25 degrees. So essentially heat is being lost. So because heat is being lost, it means our change in temperature will be equal to T1 minus T2, right? Right, what are we looking for? They said calculate its final length. So we are looking for the final length, which will be essentially the length we get after the contraction. So because remember, this is losing heat, so it is going to contract, thus losing, thus essentially decreasing in length, right? So essentially they want us to calculate the final length that we get after the contraction has taken place, right? Right, so this is 7.2 copper rod. So let's write down what we've been given here. All right, we have an original length, so I'll write this as LO for original length. Original length is 450 millimeters. All right, so this is 450 millimeters, and then at 30 degrees, so that is T1. So T1 is 30 degrees C, right? Notice how I use small letter T. Why? Because I'm writing the temperature in degrees, right? Only when you're writing the temperature in kelvins, which is its absolute state, right, do you then use capital letter T. All right, and then calculate the final. So they want us to calculate the final length in millimeters if it is cooled to negative 25 degrees. So T2 is negative 25 degrees C. All right, now we've established that this is losing heat, so it is contracting. Right, now another thing to establish is if you're going to be using the linear coefficient, or if you're going to be using the area coefficient or volumetric coefficient. So here they only spoke of the length, so it means that we're only looking at the linear perspective of contraction for this copper rod, right? Now as far as linear expansion, right, we know we get what is this, change in length, right? The change in length is equal to what? It is equal to the original length, right? In fact, you first have the linear coefficient of expansion times, now the order of this doesn't really matter, right? So you have the linear coefficient of expansion, right? I want to start with the linear coefficient of expansion for essentially, for what is this, because that is how I've written the formulas. Otherwise you can start with any quantity, right? Linear coefficient of expansion times the original length times the change in temperature, right? So this is going to help us to get the final length. The final length, because this is contracting, it means the final length will be equal to the original length minus the change in length, right? So we first are going to calculate this because we already have the original length, right? So this is equal to, now this, if you look here, it hasn't been given in the statement, right? So like I said, your coefficients or your constants are always in the question paper at the back thereof, right? So you would then go to the back of your question paper, right? When I looked there, the linear coefficient of copper, right? So because the element is copper, right, you would look under your constants, you would look for the linear coefficient of copper, right? So the linear coefficient of copper, right, is 17 times 10 to the negative 6, right, per degree, right, times original length. The original length is 450, right, 450 millimeters, times the change in temperature. right? Remember that change in temperature here is T1 minus T2, right? Why? Because this is contracting, it is losing heat, right? So this will be 30 minus, right? Remember that this T2 is negative, so meaning that this will end up being positive 25, right? For clarity, remember that change in temperature is T1 minus T2, right? And then when substituting, you have T1, which is 30, minus the negative 25, right? So what I mean is, right, these two, right, when you multiply them, when you get rid of the parentheses, right, the negative times the negative will give you the positive, right? So that is what I mean. All right, let's see what we get here. So you have 17 times 10 to the negative 6 times 450 times 30 into 25. 20 plus 25. So here I am getting 0.42075 millimeters. So this remains in millimeters. Why? Because the original length we substituted in millimeters, right? Right, so now we get the final length. Let's remember we had already established that seeing that this is contracting, this is how we are going to calculate the final length, right? Original minus change. Original is 450, all right? The original is 450, right? Minus the change, which is 0.4205, all right? And let's see what we get here. So this will be 450 minus 0.4275, right? And then the final answer, you round off to 3 decimal places. So this will be 449,579. This is in millimeters. So we leave it in millimeters. Why? Because we were told to do so. Now, if it happens that you follow the right steps, but you express this in units that are not the ones that have been specified, you obviously are going to be docked for that. You are going to lose marks, right? So always follow the instruction, right? And that is how you would approach such a problem, right? Right, now let us look at an example on heat expansion for liquids. So the one we just looked at was one based on heat expansion on solids, right? Now we're going to take a look at an example of how you would approach a problem on heat expansion for liquids, right? In fact, right, you want to look at 2 examples. All right, now let's look at this one first. It reads as follows: a 1.5 liter container full of water, right, is heated from 15 to 75 degrees, right? Now they said that a 1.5 container full of water, right, so meaning that the capacity of the container is 1.5 liters, right, and it is full of water, meaning that the container is at its capacity, right, is heated from 15 to 75 degrees. So heat is being gained here, meaning that our change in temperature, right, if we are going to have to use the change in temperature, will be equal to T2 minus T1, right? The coefficient of volume expansion of water is, so here they've given us the gamma, right, is 380 times 10 to the negative 6 per degree, right? Now let's write down what we've been given first. Right, now they did give us the, what is this, they did give us the capacity of the container, right? So saying that it is full of water, it means the volume of water is 1,5 as well, right? The volume of water is 1,5 as well. So we have the volume, which is 1,5 liters, 1,5 liters, right? And then we have T1, which is 15 degrees C. We have T2, which is 75 degrees C. Coefficient, so we have gamma as well. The coefficient of volume expansion, which is that gamma we talked about, is 380 times 10 to the negative 6. Right, this is of water, right, per degree C. Right, that is all we've been given. Right, take note, the gamma, so the coefficient of volume expansion of water has been given. If it wasn't given, you would then go to your table of constants at the back of your question paper, right, just before the formula sheet, right, and you would look for the linear expansion, right, the linear coefficient of expansion of water, right, and then remember that this is equal to 3 times the linear expansion, the linear coefficient of expansion, right? But because the gamma has been given here, we are going to use it exactly as it is, right? 7.3.1. Let's calculate the following: the volumetric expansion, right? Now here, if you notice, they haven't given us the element used for the container, right? Also, they haven't given us the linear expansion of the material of the container, right? Nor have they given us the volume coefficient of expansion of that container, right? Now, as much as they haven't specified here, right, if the volumetric expansion we need to calculate is for the container or of the water, the information we've been given suggests that we need to calculate the volumetric expansion of water, right? Volumetric expansion of water. Now remember that expansion is the same as the change in volume, right? Whether that is linear expansion, area expansion, or volumetric expansion, if you are asked to calculate the expansion from one perspective, it means they want you to calculate the change, right? The change and the expansion, or the change and contraction, is the same thing, right? So meaningly, saying that they want us to calculate the volumetric expansion under volumetric expansion, right? Volumetric expansion is the change in V, right? Change in V is equal to gamma, which is the volumetric coefficient of expansion, right, times the original volume times the change in temperature, right? And then now we substitute, and so this will be equal to gamma is 380 times 10 to a negative 6, right, times the original volume, which is 1,5 liters, times the change in temperature, right? Remember that heat here is being gained, right? The temperature is increasing, so the change in temperature will be T2 minus T1. So this will be 75 minus 15. Right, now if you punch this in our calculators, 380 times 10 to the negative 6 times 1,5 times 75 minus 15, right, we get 0,034 liters. Right, now they didn't specify if we should leave this in liters, or they didn't specify any units of measurement, so you can leave it in liters. All right, you can leave it in liters. Right, now let's look at 7.3.2. It states as follows: calculate the amount of overflow if we assume that the container's volume is not affected by heat. Give a reason for your answer. Right, so this one we don't even need to write. Right, we can just discuss based on the facts of this problem. Right, they want us to calculate the amount of overflow, so the spillage essentially. Right, how much volume of water is going to spill over, right, if we assume that the container's volume is not affected by heat. So by not affected by heat, it means that the container essentially, as heat energy is being added, right, it doesn't necessarily affect the container, so the volume of the container remains the same regardless of the heat energy being added. Right, so the heat energy being added only affects or only influences the volume of water. That is what they mean. Right, so if you can think about this, remember that the capacity of the container is 1,5 liters. Right, it was full before heat energy was added onto it. Right, so meaning that whatever volume of water that the water expands by, it is going to spill over by that very volume. Why? Because before the heat was added onto the container, right, the container was at its capacity already. Right, so seeing that the volumetric expansion of the water is 0,034 liters, it means the spillage, or what did they call it, the overflow, right, is going to be the 0,034 liters. Right, I hope that makes sense. Right, but that would be the answer, and the reason for that is the one I've just mentioned. Right. Now let's look at this one quickly. Right, it reads as follows. Right, mercury with a volume of with a volume of 300 millimeters, or 300 cubic millimeters, is put in a glass flask at a temperature of 16 degrees. Right, the linear expansion coefficient of mercury is 7 times 10 to the negative 5 per degree C, and the linear expansion coefficient of the glass flask is 10 times 10 to the negative 6 per degree C. Right, calculate the following. Now let us write down what we've been given here. All right, let us write down what we've been given. Right, so you have mercury with a volume of 300 millimeters. So the original volume of mercury, right, we are going to use Hg for mercury. Right, that is how mercury is denoted. Hg is equal to, so the original volume of the mercury is 300. Right, 300 essentially times 10 to the negative 9 cubic meters. Right, so if you were to convert that 300 cubic millimeters to cubic meters, right, so remember that what is this, 1 meter is equal to 1000 millimeters. Right, so to convert this, remember, is 1 times 10 to a negative 3. Right, 1 millimeter is equal to 1, so 1 millimeter is equal to 1 over 1000. Right, so this we're able to express like that. So instead of having 1 over 1000, you simply have 1 times 10 to a negative 3, right, meters. And then remember that this is cubed, right? And then of course 3 times negative 3 gives us negative 9. And then of course this is cubed, right? So that is how you get this, or that is how you get this value, right? Right, so you have that is put in a glass flask at a temperature. So T1 is 16 degrees C. The linear coefficient of expansion for mercury, right? So again, use Hg, right? So the constants here are given in the statement, so we don't necessarily need to go, or you wouldn't necessarily need to go to your table of constants, right? Because your constants are given already in the statements, and this is 7 times 10 to a negative 5 degrees, per degrees C. And then you also have of the flask. Let's just call this GL for glass, or let's write glass, which is 10 times 10 to a negative 6 per degree C. All right, now let's look at what they're looking for. 8.1.1, calculate the increase in volume of the mercury when it is heated to a temperature of 50 degrees. Right, so in this scenario, so 8.1.1, in this scenario, heat is being gained. So how we are going to calculate, or how we are going to express change in temperature, will be T2 minus T1. So they want us to calculate the increase in volume, right? They want us to calculate the increase in volume, right? So the increase in volume is essentially the expansion in volume or the change in volume. So they want us to calculate the change in volume here. Excuse me. So the change in volume we know is equal to gamma, which is the volumetric expansion coefficient of expansion, right? So of Hg, the mercury, right? Increase in volume of the mercury, right? Right. So change in V of mercury times the original volume times change in temperature, right? Now remember that here we are given the linear coefficient of expansion, right? And gamma is equal to 3 times that linear coefficient of expansion. So essentially you replace this with that times the original volume of the mercury times this is T2 minus T1, and then now you substitute, right? Substituting, this will be equal to this times that times 10 to a negative 5 times the volume, which is 300 times 10 to a negative 9 cubic meters, times the change in temperature, T2 minus T1. T2 is given in the problem, so this is heated to 50 degrees, so that's our T2. So T2 is 50 degrees, T1 we are given in the statement as 16 degrees, so that's 16. And this is equal to, so let's punch this in our calculators, 3 into 7 times 10 to a negative 5 times 300 times 10 to a negative 9 times 50 minus 16. So I am getting here 2,142 times 10 to a negative 9 cubic meters, right? Cubic meters. Now had you calculated this in cubic millimeters, you would get 2,142 cubic millimeters, right? And that is how you would approach this question. Right, now let us look at 8.1.2. Calculate the overflow of mercury in a 300 cubic millimeter flask when it is full at 16 degrees and then heated to a temperature of 50 degrees. Right, now notice how they didn't give us the assumption that the heat, right, the heat energy does not influence the glass flask, right? So the fact that they haven't told us that, it means we cannot assume that there is no influence on the flask, right? Because generally speaking, if you add heat to an element, right, you expect it to expand, even if the expansion is very small, but you do expect it to expand, right? So unless you've been told to ignore the expansion, right, you consider the expansion, or you always assume that there is some expansion, right? Now in this scenario, we are told to calculate the overflow of mercury, right? So the spillage of mercury, right, in a, so the capacity of the flask, if the capacity of the flask is 300 cubic millimeters, so that is to say, if the volume of mercury is 300 and the capacity of the flask is also 300, it means the flask was full before heat was introduced onto the container, or before it was heated, or before it gained energy, or before it gained temperature, or before the temperature increased, right? So before the heat was gained, the flask was at its capacity, right? So meaning that we need to consider the volumetric change in mercury and also the volumetric change of the flask, and the difference between the two will give us the spillage, right? Now we've already calculated the volumetric change in mercury, so we first need to calculate the volumetric change in the flask, right? Now the flask is a solid and that mercury is a fluid, right? So you would expect that a fluid expands more than a solid, right? That will be confirmed though by our calculations, right? So saying that we've already calculated the volumetric change in mercury, we are first going to, for 8.1.2, we're going to calculate the volumetric change in the flask and then calculate the spillage of the mercury, right? So 8.1.2, we want to get the change in volume of the glass, which will be equal to gamma of the glass times the original volume of the glass times the change in temperature, right? And then just like with the first scenario, 8.1.1, right, because we've been given the linear, right, we've been given the linear coefficient of expansion of the glass, right, you simply replace gamma with 3 times the linear coefficient of the glass flask, right, times the original volume of the glass times heat is still being gained, so this will be T2 minus C1, right? So this will be equal to 3 into, and the linear coefficient of expansion of glass is 10 times 10 times 10 to the negative 6 times original volume, which is at 300, so 300 times 10 to the negative 9. That remains the same, because remember the capacity of the flask, right, is also 300, and we already had worked out how we would express this 300 cubic millimeters in cubic meters, right? And this is the amount we came to, times change in temperature, right? T2 is still 50, T1 is still 16, that right? Yes. Right. And now we calculate. So this is 3 into times 10 times 10 to a negative 6 times 300 times 10 to a negative 9 times 50 minus 16. Right. So here I am getting 0,306 times 10 to the negative 9 cubic meters, or if you left it in cubic millimeters, you would get 0,306 cubic millimeters. Right. Right, so this is the expansion of the glass flask. Remember that we established that you would expect a fluid to expand more than a solid, which is the case here. If you look at the volumetric changes, right, of the mercury, which is the fluid, and the glass flask, right, of the mercury one is relatively higher or is relatively greater than the one of the glass flask, right? And then to calculate the overflow or the spillage, right, so you say overflow, so this will be equal to this, right, minus that. Right, and this is equal to, so you take the first value is 2,142 minus 0,306, right? And this, if you punch in your calculators, 2,142 minus 0.306, this is 1,836. And then it depends if you express this in cubic meters or in cubic millimeters. For cubic meters, this will be times 10 to the negative 9 cubic meters, or in cubic millimeters, this will be 1,836 cubic millimeters. Right, but that is how you would approach such a problem. Right, I trust that you found this helpful. Right, in the next video or in the next session, we'll discuss gas laws. Right, again, I hope you found this helpful. Yeah, see you in the next one. Cheers.